Okay. All right, so last week we were talking about the charges on atoms and how we know that from what group they're in and how many valence electrons there are. Today I handed out this periodic table of ions, and this tells you the charges that an ion can have, and you can use this on your test. Okay, you could use this as well as your normal periodic table on your test. And so the ones that you should be able to memorize were like 1A. 1A group has one valence electron, and it only has one, so it's easy for it to lose it. So that goes to a 1 plus charge in the 1A group. And if you look at column 1, they're all plus 1. And then if you go to the 2A group, it has 2 valence electrons, and it's fairly easy for them to give up those 2 valence electrons. So those are all 2 plus. Now, I would like some help labeling my periodic table. If you guys could do these stickers for me, the 3A and the 5A. Let's see, just put these up. So 3A jumps all the way across over to boron, and then see if you could put those where they go. Here you guys go. Put those on top. See, I already labeled what group 1A and group 2A over there. And now remember that group 8A is called the noble gases, and that's because it has 8 electrons, and they're noble because they're very happy and complete. Most atoms are happy with 8 electrons. We'll talk about some exceptions in the next module, but for now, we're going to do that. Okay.
I don't think so.
Group 7A is called the halogens, and that has 7 valence electrons. Well, it's a lot harder to give up all 7 of those. There's 7 of them pulling in towards that nucleus, so they're held on more tightly. It would rather take them to go from 7 to 8 and make complete. Okay. 6A, same thing. It would rather take electrons, so you'll see that most of the 6A groups on the table of the ion charges are negatives. Okay, but then when you go to group 5A, you can see the ones at the top like to take electrons and become negative, but the ones at the bottom are okay giving up electrons. We're going to talk today why some of those those ones would rather give up electrons. And it has to do with the size. As you go out in those shells, it has more shells. And as you get out further away from the nucleus, it's easier for them to give up electrons. Okay? All right, you need to know that the transition metals, let's do group 3, the transition metals next. I want labeled. Okay. The transition metals is this yellow. Can you, Carrick, turn? Transition metals is this group here. There's a little pan stick there that you could turn. This yellow group here, this is the transition metals. And we're going to label those. These are the B columns. And then, okay, so then these are metals. We have a fun thing with gallium today.
Oh.
If you know gallium, you're like, ooh, fun. And then these yellow ones are the metalloids. They're also called semiconductors. They sometimes act like metals, but know that these are the metalloids. The metals are on both sides. Okay. These are the transition metals. Okay. And then noble gases. Know that. Non-metal. Okay.
Use a little.
Use the stick. Okay. You're going to make Matthew seasick there. Okay. So, so let's review from last week where we did if both charges have the same numerical value. Okay, let's do an example. Okay, let's do strontium selenide, some unfamiliar chemicals. strontium selenide. All right, look at your table of ion charges, and you will see that strontium has a 2 plus. And selenide on the other side, on the opposite side, remember metal and non-metal are often far apart from each other. And selenide has a 2 minus. Well, those balance each other out so that those charges cancel out, and so the chemical formula is just SRSE. Okay? But if the charges are not balanced, you got to do something else. Okay. So let's say I wanted strontium chloride instead. So strontium still has a 2 plus.
Off screen.
And chloride has a Cl minus. Okay? To make the molecular formula, I'm going to switch crisscross. Right? This is, remember, a 1 minus. Okay, and I get strontium with a 1, don't write the 1, and chloride with 2. You guys got that? Crisscross if your charges are not equal. That's what Dr. Wild tries to describe in the book, but there's no diagram and it's difficult to understand him. So, all right. Okay, that's his review from last week. We are going to talk about periodic table properties next. Switch back to here. Oh, wait, hold on. That transition metal exceptions. So in transition metals, you notice in the middle, these are the transition metals. Did we label the B's? We did. We had spacing out. Here, guys, this is out again. Okay.
It goes in a weird order.
It goes in a weird order.
It's like
It does.
1, 2, 5, 6, 3, 3, 3, 7, 8.
Okay. All right. Here we go, guys.
It's not on the actual periodic
So
table.
the B's go in a weird order, 1 and 2. You just put 1 and 2 here, and then you can go 3, 4, 5, 6, 7, and then 8 covers the last 3. 1, 2, 3, 4, 5, 6, 7. All right. Here, guys, help me out again. Okay, help me out. Okay, so let's label the. Let's see, the 8, 1, 2. Okay, 8 covers these 3 rows. 5.
Have fun finding 7.
Theoretically, you just count 5. I'm
I am What?
I'm these.
All right, and remember that those pink rows on the bottom, the lanthanides and actinides, those actually insert into this little gap here.
Trying to make it straight. Whoever put down 6B is a double.
But then what about?
3, wait,
Who did that?
oh yeah, to move them over, is that, yeah, there you go. That's 3B for sure.
And I'm assuming that 4B should
4,
go-
5, because 8B covers 3 columns. I just didn't have
Yeah,
3
this-
ABs.
I'm really good at placing stickers, so they're gonna be hard to take off.
Okay, so on your periodic table of ion charges, you'll notice in your transition metals here in the middle, which include this lanthanides and actinides. So sometimes you can find an expanded periodic table on the internet, but it doesn't print out well on a piece of paper. But just think those lanthanides and actinides insert in there and everything pushes out. It would make a really wide periodic table, difficult to print on a piece of paper. Those are not separate rows. They're period 6 and 7 elements that go in the transition metals and have multiple charges. Alright, so that's when you use the Roman numerals in naming. So if I want something like tin chloride, I need to know which charge of tin. So it's going to be written, switch. It's going to be written in words like this. Tin for chloride. Okay. And the element for that, if I look at tin, this tells me that tin has a +4 charge. Okay, so if tin has a, whoops, not tin, let me put the element. Tin has a +4 charge, and then Cl stays the same. Chlorine, it still has a 1-, and I'm going to crisscross. Okay, so I end up with tin chloride. Looks like that for the molecular formula. All right. So know how to do that if you're given the molecular formula, be able to put it into words, knowing what the charge is. You'll have to put this Roman numerals in there too. Okay? And if you are given the words, be able to give me the molecular formula. All right. Now we're moving on. Oops. What is that? Okay, periodic table properties. There's some general trends on for the periodic table. That's why it's so helpful to have it all, it's so organized. And I'm going to show you something that it makes it easier for me to remember. Figure 8.1 in your book. I've just gone ahead and written in my book. And so he does increasing ionization potential this way and decreasing this way. I like to do increasing this way and increasing this way. It's the same, it's saying the same thing, just saying it differently. For me, it's easier to know that if I see the arrow pointing across the table increasing and the pointing up the table increasing, I know that my general trend is this way, going up to where both arrows are. I know that this is my lowest ionization potential going up to my highest ionization potential. Okay? So in fact, what I did here is I put increases, an arrow right here on my diagram. That shows me that it increases diagonally across. And I circled fluorine. Fluorine is the most electronegative or the highest ionization potential element. All right, so you need to know this trend. And ionization potential versus electronegativity, he covers both in the book. Just know that ionization potential is an amount of energy. Remember we talked about energy at the beginning of the semester, we talked about joules and things like that. So ionization potential in a higher chemistry class would be used for doing calculations. It's a number. It's an amount of energy that's needed to move electrons away from one atom, okay? Whereas ionization potential is a relative term. How easy is it to remove electrons from specific elements? So everything on ionization potential is relative to fluorine. Fluorine's the largest ionization potential at 4, and then you go down to lower ones, and people look at it's a relative difference. You'll look at the relative difference between them. Okay, is it going to make an ionic bond or a covalent bond? In higher chemistry classes, you would be able to know, if the difference in electronegativity is more than 1.7, then it would be considered an ionic bond instead of a covalent bond. You don't need to know that for this class. Just know the general trends of ionization potential And electronegativity, they're the same. They're both going up towards fluorine. Okay, diagonally. Okay. So, and yeah. So it increases from this side, from the left to the right, because as you go from the left to the right, you get more electrons, and more electrons are increasing the pull on the protons. It becomes more difficult to take them away, like I was saying before. So, and he says, and here it decreases from the top to the bottom, or it increases from the bottom to the top. Either way you look at it, it's the same. Because they have more different energy levels. They're getting further away from the proton, further away from the pull. It's basically getting bigger as you go down, so they're less electronegative. Okay, and it's the same reason for electronegativity as it is for ionization potential. All right, the other trend that we are looking at is atomic radius. And I did the same thing on my book here. Atomic radius increases down here, and it increases from right to left. It's opposite of electronegativity. So that the general trend is going from the smallest elements to the largest. Francium down here on the bottom left corner is the largest. So I circled francium. All right. No, you're going from smallest to largest, from the right to left diagonal. Okay. Eric, I don't know if there was a close-up of these drawings that I altered. If you could do that for Matthew, zoom in on that. Let's zoom in on each of those diagrams.
It's freaking
Okay.
Which one?
All right, so last week we worked on Lewis structures for atoms, for a single element. This week we're going to work on Lewis structures for covalent compounds. Remember that a covalent compound is a non-metal and a non-metal, and they are sharing electrons. They're not giving them up. Okay, so they share the electrons in the bond that hold them together. And review how to name them. We are going to do that today too. Let's go ahead and start with the naming review. And Matthew will send you this worksheet. So you guys are gonna go through and just spend some time, see if you could give me in the first section, give me the molecular formula. In the second section, give me the name and words.
Great.
Just do the thing.
And then we'll go through the answers in a few minutes.
I need. Thank you.
Okay, I ended up with 2 extras. Did everybody get one?
Chemical formula?
Turn these into these.
Yes.
That should be helpful.
Why didn't you get like a matching thing?
That would make fun.
It would be more fun and it would have been easy.
It's actually named for it. Plus,
Carrie, can you go ahead and pause the recording? We don't need it on.